And I strongly recommend you start writing stuff down, because I'm asking you to solve this, and I don't think anyone in here can do the whole thing in their head.
So 6 particles and 9 different combinations. Wouldn't that be a 6 to the 9th power?
No,
It's 9 to 6 power.
no,
Oh.
If you just swap the particles on the second one, swap those two with 2 on the bottom, are we counting that as a different combination?
oh, if you swap those two?
Yeah,
No,
That's
that,
good.
count that as the same.
okay.
I've never.
I will tell you, if that were different combinations, then there's 2002 of them, different ways of doing it. And I wanted to avoid the 2002 version.
Okay.
So
Wait,
there's-
isn't it just like,
I don't think I've ever done a partition problem before.
Now's your chance.
no, wait.
So we have
Okay.
6 particles, but there could be 9 ways that all of them could be. So there's 6 particles, but there's 9 different combinations. But each of those 6 particles could be in 9 different combinations.
Think of it this way, there's 6 people in here, and I have $9 to spread between us. How many different ways can I spread 9 $1 bills among 6 people?
Oh.
And giving $1 to you or giving $1 to Con counts as the same. We are indistinguishable.
It's 9 times 8, 9 times 7, times 6, times 5, times 4.
Much smaller than that.
It's not many.
Trying to do probabilities, permutations and combinations. There is a formula for if the particles are distinguishable. In other words, swapping these two would count as something different. There is a way of doing that with combinations and permutations. However, I've not seen one for this. And because I'm asking you to do it, it is a relatively reasonable finite number. It's not, I'm not asking you to, it's well under 100.
54.
Did you get 54?
Multiply 6 by 9.
Yeah, no, it's not that simple.
Okay.
Then I probably would have seen the formula. We can do it piecemeal. What's another combination?
4 zeros and 2 and 7.
Pardon?
4 zeros and 3 and 6. 4 zeros and 4 and 5.
All right, so I'm just gonna simplify it down to 4, 1, 1, 4, 1. And you can do the next one, 4. The number that I just wrote in orange over top of it, that's if, flipping two of them counted as something different, that's the number of different ways. So this would count as, there's 30 different combinations if the 6 particles are different.
To the 21?
No, how'd you get 21?
I wrote them all out. But
So
I
what
may
you
have
got?
skipped some. Well, I started, okay, ignore this one. I basically said like, okay, how many combinations if we just put one particle on? So 1 for 9. How many if we put 2? We have 8 and 1, 7 and 2, 6 and 3.
Okay, that's the ones that we just did, okay.
So then for 3,
Alright, so let's get those down. So you had, so that means you have 3 at 0.
yeah,
Right.
so I did 7 and then 2 1s. And then 6, a 1 and a 2. Then 4, or sorry, 5, a 2 and a 2. 4, 3 and 2.
What were those again?
4, 3, 2.
4, 3, 2?
And I
Yep.
think that's it for that one. Right, for 3.
You were missing
Skip
1?
Can you do 3 on 3?
Oh, yeah, you can do 3 on 3. That explains it.
And there's
Is there another one?
1, 2, 3, 4, 5, 6, 7. There should be 7 of them, and we got 5.
7 of them.
Also, if I kept 1 down here and I moved that up 1, and then that
Oh, yes.
down 1, so 3, 1, move that up 1, that down 1. Let's just make sure I didn't lose track, so 3, 5, and 1, and then 3, that moved up 1, that down 1, we already got the, oh, there we go, 3, 1, 2. Okay. So you basically have the technique there, let's keep going. And again, let me make sure I didn't miscount there, so 1, 2, 3, 4, 5, 6, 7. Okay, we got 7 there. So now we have 2 here and 4 to play with.
You want me to go?
Yeah.
6 and 3 1s. Or sorry, what did you say were?
We have 2 at 0
Yes,
and 4 to play with.
yes, so 6 and 3 1s.
I'm losing track of my numbers here. The 0, sorry, 0, 1. Alright, so you have 1 at 6 and 3 at 1, okay?
1 at 5, 2 at 1, and 1 at 2. And then I'm trying to figure out how that rule works, but okay. You have 1 at 4, 2 at 1, 1 at 3. 1 at 4, 1 at 1, and 2 at 2. Do you want to say it?
Yeah. You do 1 at 5, 1 at 3, and 1 at 1.
1 at 5, 1 at
3,
3.
and 1 at 1. Whatever.
So basically, wait a second.
1 at 5, 1 at 3, and 1 at 1. that's for,
One,
5 marks.
2, 3, 4, 5, 9.
Did
I have 5, 3, and 1.
Oh,
We have that one.
we do, okay.
Okay.
That's with 3 and 0.
Yeah, my bad.
Ah,
Is that all the fours?
I thought that was,
I think it's all the fours. We're sorry.
so every one we move up, we gotta move another one down, so let's see. 1, 2. We're missing 1.
1 at 1, 3 at,
We're missing 2, I'm sorry. 1 at 1,
3 at 3.
then we're already at 10 energies.
Oh,
Alright, so that came down one, got those closer together. And then at that point they would flip, so go to the next one, brought that up. That down. And so if we brought one of up, one down to 1, 1, 2. That's 3, 6, 7, 8, 9. Okay, there's another one there. And then, we already have that one already. Two, three, four, five. So what are we missing? So we got the 2, 3, jump to 1, alright. 2, 2. So we're good on that one. We got the 2 of those up.
1 at 6 and 1 at 3. No, never mind. Forget that.
And then 2 here. And then 1 at 5.
That's on, wait.
Pardon?
hold on.
Oh, we lost the particle.
Yeah. Cause I think we have that one already, don't we? Or-
So that's 6, and then 1 at 3, there we go. Now we have 6 particles. This is 3 at 2, that's 6 units, and then plus 3. And I think that's it. We count. Okay. Then we got 1 here, and 4, and then this would be at 5. Then 1, 3, 1, 1. 1, 3, 2. Double check, we got 6 and 3, all right. And then 1, 2, 1. That's 1, 2, 3, 4. So again,
Shouldn't there be, wait,
1, 2, 2. So we got 1, 2, 3, 4, 5, 6, and then 1 at 3.
do we have, 3 at 1, 1 at 2, and 1 at 4? Yeah.
Yep, that's this one.
Okay.
I feel like we're missing one of the ones. 1, 2, 3, 4.
We're missing the 5. 5 and 4. No, what? I have 4, hold on,
So this is
I'm losing that.
0, 1, 2, 3, 4, 5, 6, 7, 8,
1 at
9.
5 and
Oh, we need, 4 2s and a 1.
There we go. And then 0 down here, now I have 6 playing with, so I got 5 right here. And then 1 at 4, 0, 4, 1, 1. 0, 3,
1
Sorry, you were saying?
I'm still thinking.
I think that's it. So I got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6. I got 26 different combinations. If the particles were different, then the number, if you work through that, this would be 120, 120 of these, 120 of these, 60 of these, 60, 60, 20 combinations there, 60, 180, 180, 180, 180, 60, 30, at this point, 30, 120, 60, 180, 30, and 6, 30, and 20. All right. Unless I made a mistake, this should add up to 2,002 possible, if they're distinguishable. Well, let's concentrate on the 26 for right now. So, the classical theory, it is assumed that any one of these is possible. So I got my 9 energy, I got 6 particles, so the number of possible 0 energy states is 59. So if you added all these up, 59 possible locations for that. There's 40 possible positions where it would have an energy of 1, 23, 14, 8, 5, 3, 2, 1, and 1. There's only, so out of the total that is there, 156. So there's 156 different positions that a particle could be in. 59 of them are here, 40 here, and so on. So on average, if I took just one of these states, because just one of these states can exist at a moment, on average, so 59 divided by 26 possible states, 2.2692. So on average, I would expect, if I did a whole sampling of all these different states, I would expect a little more than 2 1/4 particles on average to have no energy at all. 1.5385 on average. And yes, I'm gonna write all these numbers down because we're gonna do something with it in just a second. So, like 5385, 0.3077, 0.1923, 0.1154, 0.0769, 0.0385, 0.0385. So that's the average number of particles. Now, what I want us to do, want us to do, is first figure out what is the total energy. I know it's going to be 9, but let's just sort of confirm that. So on average, I'm expecting 0.0385 particles of energy 9. So if I multiply this by 9, multiply this by 8, this by 7, this by 6, this by 5, this by 4, multiplying by the energy, 3, 2, 1, 0, and add them all up. If somebody would be kind enough to do that, probably more than one. And since we're doing a weighted average here, well, a weighted sum, we can then find the average.
$765?
That right there?
Yeah.
.0769.
69.
Is it 3077? At 4?
.3077, yes. Or .307 flying fish. Dolphin.
I see it as a dolphin. What is it? 2, 8, 8.
88, I'm pretty sure that's 4 there, 8846. Alright, so note to self, right more deeply.
.0007
Alright,
is what I got.
and so there's rounding issues there.
What'd you get, 9.0043?
No, 0007.
Oh, I got 9.0043, but
I think we can both say that it's close enough to 9, which is the energy that we had. So my total energy